Greetings and welcome to today's educational program, Improving the Effectiveness of Visual Inspection by Ted Schorn. This is your moderator, Doug Wood, with ASQ's Quality Management Division. This webinar is being brought to you by the ASQ's Quality Management Division and the ASQ Inspection Division. We have the distinct pleasure of hearing from Ted Schorn today. Please join me in welcoming him. So, Ted Schorn is a senior member of ASQ and has over 40 years of quality management experience, having worked in medical, aerospace, and automotive quality. Ted currently serves as the Vice President responsible for quality and product development for Enikki America Incorporated. Ted is the principal of Schorn Consulting, LLC, and has written 3 texts, Improving the Effectiveness of Visual Inspection, Understanding the Wheel Fastening System on Trailers, and his latest book, released in 2023, Process Control for Engineers. Ted teaches and constructs courses for the Cast Metals Institute and has been awarded the Gold Medal and Scientific Merit Awards from the American Foundry Society. He's a frequent conference speaker and serves as president of the Lean Network Incorporated, a nonprofit corporation focused on quality improvement through the application of lean manufacturing principles within the Honda supply chain. And so without further ado, it is my pleasure to introduce Ted Schorn. Ted, the floor is yours.
Great. Thank you. Well, we'll get started right away. I'm pleased to be able to have this opportunity to talk to you about human visual inspection. I hope you understood that we were talking about inspection by people and not by machines. Despite the higher degrees of automation that we see in our facilities and lots of talk about Industry 4.0 and so forth, human visual assessment still remains, for many of us, a critical element, even if that's not in a repetitive setting, but as spot checks and audits and those kinds of things. And specifically, cosmetic appearance is still assessed primarily by human visual inspection. An illustration of that, of course, is the photograph that you see on this slide. That's one of our products made at the company that I serve. And the complexity of this shape and the need to inspect it for a variety of cosmetic deforms, as well as the challenge of picking out those defects against a complex background, make this perfectly suited for human visual inspection and perfectly ill-suited for machine vision, and even the variants of machine vision that incorporate software with artificial intelligence or neural net processing. And that's because machine vision still has not reached the level of capability of competent human inspectors. And of course, there's an emphasis there on the word competent. And that's part of the reason that we're talking today, is to try to help us all to do a better job of preparing our human inspectors to do the job of visual inspection. I might add that I have written a more extended journal article on the matter of automated inspection or machine vision, and you may wish to get that and find out a little bit more about that topic. I understand that many of you are probably investigating whether machine vision options are appropriate given the nature of the challenges with human visual inspection, and I think this paper might provide some guidance. Visual inspection has been a subject that's been talked about for a long time, and probably if we know anything about it, we understand that 100% visual inspection is not 100% effective. Some of you probably are walking around with the thought that 100% inspection is about 80% effective. I want you to know that that was actually Duran's estimate back in 1935, And the source for that quote is on the slide. It turns out that Joe Duran was an optimist. I have in my possession and cited in my book scores of journal articles where research was done on miss rates and false alarm rates associated with human visual inspection on everything from tennis balls to underwear to machined nuclear reactor parts. And the range of miss rate and false alarm rate is on this slide. It's a very sad story. And if you were to take those miss rates and false alarm rates and actually calculate for a given product lot what the overall effectiveness would be, it many times would be even less than 80% effective. So that's a problem, and we feel that problem acutely, and some of us feel it less acutely because our customers really don't know what they're looking at or aren't as critical as we think they are, and so we're over engineering our specifications. But believe me, if you were to take the time to measure the effectiveness of your visual inspection, you might be surprised by the results. And so we're all here to try to improve that. And, you know, as a career quality guy, we need to apply quality engineering to the inspection process itself in order for us to make any kind of improvement. So how do we do that? Well, before we get to that, I want to emphasize the fact that actually measuring the miss rate and false alarm rate of your particular operation, I think that's really important. And the reason is because you're going to discover the impact that those errors have on your operation. I want to illustrate that by taking this example. So suppose we have a situation, this is one taken from a client of mine. They have a basket of 1,000 castings. And let's suppose that those castings, within that pile of castings, 5% of them are defective. And let's suppose that that lot that represents these 1,000 pieces is given to an inspector who has a 15% miss rate and a 5% false alarm rate. Now we know the truth about this lot. We know that there are actually only 50 bad parts in there because that's 5% defective, and that there are 950 good parts. But when the inspector finishes his work with those error rates, what we find in that inspection report is that he will say that there are 910 good parts and 90 bad parts. And so you might feel a little bit bad that you're not getting quite as many good parts as you expected. And you might feel that perhaps he was a little overcritical because there's 90 bad ones when we thought there might only be 50 bad parts. But the actual situation is far worse, because the 910 parts that this inspector described as good actually aren't all good. And that's the result, of course, of miss rate. There are some bad parts in there, some of which, in fact, 15% of which, he did not find. He called good instead of bad. So those are in that pile of good ones. And he doesn't see all the good parts that are in there as good because he has a false alarm rate. He has a tendency as well to judge some defects more harshly than the specification would require. And so in this 910 good parts, only 902 and a half are actually good. And if you translate that into a percent bad, if you were to take those good parts and sell them to your customer, you would discover that you're about 0.8% bad, or over 8,000 ppm in terms of quality. That's not so nice, whether you're in automotive or aerospace. On the other hand, the 90 bad parts, most of them are bad. Actually, not even half of them are bad. 42.5 are actually bad. And then there is a very large number, 47.5, that are good, but were called bad. One might wonder why there's so many good ones that got put in the bad pile when the false alarm rate was only 5% as compared to a miss rate of 15%. And the answer to that question is because we presented to that inspector so many more good parts, which is typical of inspection operations, at least I hope it is for you. And so as you present all those good parts, some of them, and in absolute terms, a large number of them will actually be called bad. Now, if you think about the consequences of these improper decisions, these errors made in inspection, first of all, we're unhappy and our customers are unhappy because they're getting bad parts despite the fact that we did 100% inspection. That may or may not be a surprise to you. What is probably a surprise to you is the significance of the false alarm rate, because now we think that we're worse than what we actually are. We think that instead of 5% bad, we're actually at more like 9% bad. And so we're going to be chasing the causes of things that don't actually exist. We also have a production control problem because we started with 1,000 parts, and we might have given ourselves some allowance for some fallout, but probably not at a rate of 9%. And so production control is very challenged to meet its requirements because of these errors. And then, of course, the parts that are called bad, depending on whether they are scrapped or whether they're sent to some rework operation, that's additional money in processing and loss and handling damage and so forth, even if the parts are finally discovered to be okay. It's a very horrible situation, and it's one that goes hidden because we believe our inspectors and we think that they're diligent. And we don't really expect, most people, most clients that I work with don't expect there to be much false alarm rate at all. But even a very small false alarm rate can have pretty significant consequences, as you can see. It turns out that people believe things about inspection that just simply aren't true. And I won't read all this list. You can read it faster than I can say it, but I hope you resonate with a few of these statements, and you may actually still believe some of them and think that I don't know what I'm talking about. And the way to prove that is to do the experiment yourself, or to spend time in journal articles and research trying to see what people have actually done in terms of experimentation. But every statement on this slide is false, proven by experiment and good research. And so these kinds of shortcuts to improvement in inspection aren't going to work. So we've got to do something better. And what we're going to do better is we're going to first apply quality engineering principles. We're going to look at inspection as a process. And the research on human visual inspection has identified that the inspection process itself goes through a cycle, as it were, identified on this flow chart. I'm going to play a little video. This is a video of the inspection operation taking place in our factory. And it's a little bit dated, but you can kind of follow along with what's going on. Obviously, the inspector is looking at aluminum wheels, our product, and try to follow the model as we go through it. She's already slid some parts over into her area, so she's obtained the part, and you'll see her orient the part, and then unfortunately the video doesn't show her eyes, but if you were able to see what her eyes were doing, you would see that as she orients the part, she does a visual search over the area of the wheel that is put in front of her so that she can see it. If she detects a flaw, if she sees something that is unusual, then her brain is going to determine what it is, and then it will determine whether that anomaly, that thing that has captured her interest, is acceptable or not on the basis of some criteria or another. And if it is indeed acceptable, she will continue to go to the next orientation of the part, because the part in 3 dimensions with all the surfaces cannot be seen all in one orientation. Not too many of us are inspecting 2-dimensional objects. We're all inspecting 3-dimensional objects. So we orient the part, and then we go through the cycle again as many times as is necessary to complete the process. And then the part is moved off. It's dispatched to its location where it belongs, depending on its status. And then some information is recorded. So let's follow that as she works her way through this process. You'll notice that she uses her hand as a pointer in some respects. You'll also notice that she rotates the part towards her, not away from her. That's a trick in visual inspection. Here she's obtaining parts. She scans the part, and that begins a timer, which helps her to maintain the pace of her choreography, because it's very important for her to spend a certain amount of time on each of the critical areas. Now, I won't represent that she's doing things perfectly, and we've made a few improvements in the layout and so forth since then, but you get the idea. Quality engineering inspection means optimizing each of the steps in this process that's on our slide. And the 2 most important are visual search and the decision-making process. And of course, that makes a lot of sense. In order for us to determine if there's something wrong, to find something bad, some defect on his part, I've got to be able to see it. And so visual search is critically important. But then once I see it, I have to decide what to do with it. Is it good? Is it bad? Is it borderline? What's the decision that I need to make once I see something? And that is also of great importance. And we'll talk about both of those. Now, very quickly, all the other steps can and will contribute to problems if they're not properly engineered. But in the time that I have today, I don't have a whole lot of time to talk about all those other aspects. Buying the book, sorry to be so shameless in its promotion, but the book has a chapter on each of these sections. And so we go into quite a bit of detail about them. Well, let's just play for a second. We've got time for it. So visual search, it's not trivial. And when we're looking for paint defects or little casting defects or some machining aberration, we're trying to hunt for a very small defect in a confusing field. For fun, I like to do picture puzzles. Takes my mind off things and just kind of brainless entertainment that I enjoy. Have you tried this experiment yet? Have you found out how many edge pieces is in this colored picture? You don't have the opportunity to talk back, and I'm not going to collect answers, but you'll have some number in your head about how many you found. And I'll give you just a few seconds more to look at this picture. And as you're looking at it, I want you to be conscious of the manner in which you're searching. Are you using a raster pattern? In other words, are you going back and forth as if you were reading to look for these straight edges on these puzzle pieces? Or did you start in the middle and go around in a circle? Or perhaps did you start at one edge and go all the way around the edge, and then your eye got attracted by some colorful piece or something that drew your attention that perhaps you could search in that area? In the absence of direction about how to search, humans do a couple of things. They look at the center of interest, and in this particular photo, there's no particular center of interest. And so what they do in that case, and this has been proven again by quite a bit of research, we trace along the edges, and then we look for the most unusual or colorful thing that attracts our eye, and we circle about in that area. It's often a very random search, and if we have a lot of time, we'll be a little more systematic. But if we do not have very much time, it's quite random and chaotic, and it's very easy to miss things. I hope you all got 7 straight edges. But in order to have even a glimmer of hope of finding all those edges, we have to have a systematic search pattern. And that's the point that I'm trying to make. And it's one of the things that people seldom communicate in a work instruction about inspection. At best, most work instructions just describe the what's good and bad, the criteria for acceptability, and that's about it. So how do we see what's going on in our brain and what's going on when we're searching, and what actually is happening so that we can kind of engineer this? Well, literally, I have entire books on the subject of the movement of eyes during search. It's really incredible. I would never have thought, but it's a very important subject, both in terms of ophthalmology as well as in terms of searching. And the military has done a lot of work, supported a lot of work to try to improve searching. For example, searching for a submarine when you're on a destroyer, looking out at the waters out in front of you, or in an aircraft looking for enemy aircraft. So what happens when we search? Well, the first thing to remove from our brains is the concept that we see as if we were a video camera. We do not. We see as if we were a 35 millimeter photo kind of camera. We see in snapshots. And those snapshots are referred to as fixations. And in order for us to capture the image in our brain and actually dwell on it and deal with it, it takes about 1/3 of a second to do that. And then there's a rapid eye movement to another area of our interest, and we fixate at that new location. The scan path can be defined, and either defined by habit and experience, or it's a random scan path. But the scan path is basically photo, fast move, photo, fast move, photo. It takes about 1/10 of a second to get to the new position. And it's not always the same distance in that 1/10 of a second. It depends on how rapidly our eyes are moving and our eye musculature and things like that. But we're taking photos and we're piecing them together in our brain. We use a system called an eye tracker, and there's several different ways, and the picture's actually a little out of date because they're a lot fancier now. But when I was first doing this work, I used a system that looked very much like this photo, and it shows on a computer screen where a person's putting their eyes, and very interesting. So almost all the information that we get while we're searching is in the fixation phase, which makes sense. We're rapidly moving from photo to photo. And those fixations take about 90% of our search time. But it's really important for us to recognize that if we move so fast that we cannot spend at least a third of a second dwelling on an image, it will not be effectively recorded in the brain, and it will not be able to be evaluated for defects or anomalies. Now, how much can you see at one time? You know, when I was showing you that slide with the puzzle pieces on it, your your sense was that you could apprehend the entirety of that image at one time, but actually, in terms of useful inspection area, it's actually quite a bit smaller. In fact, when you hold something at arm's length, you map a area of good resolution to only about a 3x5 card, and that's only if you're using both eyes. That's a pretty small amount of area where you have good visual discrimination. And that little 3x5 card image that you can have in your head, that's about the effective area that you can see in each of the fixations, assuming decent vision. Now, that's the size of that 3x5 card actually depends on a few things. And a 3x5 card is kind of an optimal size. It assumes that the object's been properly illuminated. It assumes that the things that you're looking at have pretty good contrast between, the defect and the background, and that the size is within our ability to resolve. And again, I could go through some trigonometry to explain the size, the minimum size that you can see with a certain degree of vision. And all that's covered in the book. And also, it matters how far the object is from a person's eyes. But basically, the effective viewing area is about a 5-degree arc from center. And that 5-degree arc mapped over both eyes represents, at say 18 inches or so, about a 3x5 card. We refer to that 3x5 card as the area that we can see well. We refer to that as the visual lobe, and its size is certainly a factor in visual search effectiveness. Another factor which we can engineer is the search pattern. Not only the efficiency of that search pattern, but the coverage and the extent of overlap in, for example, critical areas. Time has an enormous amount to do with the method by which we search and our effectiveness. And clearly there are constraints. We got to provide a certain amount of time for each of those 3x5 cards, or we're just not going to capture the information. Part complexity is another factor, of course. And finally, while multiple defect types, as we're searching, if you remember the model that we had on the slide a couple prior, the first thing we do is we see something that attracts our interest, something that's considered different or an anomaly, and then we decide what it is, and then finally we decide whether it's okay or not. That means that visual search is only looking for unusual things. So it doesn't really care what defect type. What matters about defect types is that some defects are much more visible with a certain orientation of the object relative to our eyes than others. For example, if you want to see texture, you don't want to look straight on. You want to look at it off to the side. You want to have side illumination. And so multiple defect types affect visual search effectiveness, especially if they're not quality engineered and planned. Well, there's an enormous amount of additional information we could talk about, but these are the main factors of influence of this very important thing called visual search. And can I just call to mind the last time you called out an inspector? Perhaps you had a part returned from a customer. You brought the part came back to you. You brought it to the inspector and you said, Ralph, how in the world did you pass this? I never saw that. I would never pass anything that looks like that. And indeed, Ralph's right. Ralph just didn't see that defect. Most miss rate problems are the result of poor visual search. And don't blame that on the inspector, blame it on the quality department for not having planned to do an appropriate visual search that plans a choreography so that all the critical areas have the opportunity to be seen and to develop in the inspector the habits of looking at those areas as they are presented to them in the choreography of that inspection routine. Well, so we've said enough about that. We'll talk next about the second big factor of influence in terms of what is inspection error. And that is making the right decision once one has seen something. Now, we've got to make a judgment, and we assume, we quality guys assume that if we provide objective criteria, that will be followed. But actually, there's a whole nother realm of subjective criteria that human inspectors consider when making a judgment. And those factors have to be engineered, have to be planned for every bit as much as the objective criteria. Let's talk about objective criteria first, and then we'll talk about subjective criteria. And if you want to know some more about human error in decision making, particularly as it relates to visual inspection, I have a whole nother paper which is published in 2020. That's 2 years after my book came out in 2018. So it's got additional information in it, and I think it's helpful. So in order to teach, in order to communicate where the line is between good and bad, because that's what we want, right? We want to clarify what is acceptable and what is not, so that there's clarity in the inspector's mind. The inspector does not generally have time to refer to a work instruction or some criteria sheet that's got 3 or 4 pages and a bunch of small photographs on it. They don't have time to do that typically in the cycle time afforded to inspection. So they have to understand in their head what is okay and not okay. And that means providing them with a memory device for the rules. Well, the best memory device is to teach why the rules are the way they are. Make the rules make sense. Teach about the functionality of the part, teach about how the part is used, explain why such and such has to be true about the part and that it has to be rejected if this or that is true. The second thing is to make sure that it is clear what exactly determines what is good from what is bad. What exactly are the limitations? Is it size? Is it contrast? Is it aspect ratio? What are the things that make this unacceptable? If that is not clear, their decision-making apparatus will take over, and then they will be making judgments on the basis of subjective criteria. Now, the subjective criteria are extremely important. And in the literature, it's referred to as payoff. It turns out humans are really good gamblers and they play games well and they want to win. And in inspection, they also want to win. They want to get a pat on the back by their inspector. They want to have quiet days where nobody yells at them for screwing up or doing something that would cause a problem. And so they figure out, on the basis of their understanding of what's going on around them, what is the best decision to make about something that's perhaps questionable or borderline. Imagine an inspector who's just sat through their morning line meeting and everyone in the room has gotten chewed out because a bad part got to the customer. Well, they're going to take that into account as they begin their inspection, and they're going to probably be prone to a few more false alarms because they're not going to want to pass anything that's remotely questionable because it may come back on them. On the other hand, perhaps the production control supervisor stomps through the inspection area looking for parts that may be acceptable or somehow got left behind, and because he's short on a shipment. Well, the inspectors see that kind of behavior, hear the rumor mill or the gossip, and understand that the company's in trouble and needs to make shipments. And so they may decide to help that process and let some stuff go that they wouldn't otherwise have. There's surprising power in the subjective aspect because we are talking about human visual inspection. Some other things that influence decision making is the incidence rate of defects. Imagine taking a 50 question true false test, and you're down at question 40, and so far all the test questions have been answered true by you. You think there's something must be wrong, and so you begin second guessing things. And so suppose that you feed your inspectors a very large number of good parts in a row on a given day, when that's quite unusual. Maybe the normal defect rate is 3% and there's been hardly a 0.5%. They'll start thinking they've been missing things, and they will look more deeply into what they're inspecting, and they will find things that aren't there because there's this abnormal, out of balance situation that they feel in their emotions, and they will self-correct. And so it's extremely important that we focus on helping the inspector to understand that their job is to make decisions about acceptance that are completely based on objective criteria. And there's ways to do that. Pacing and time pressure, stress and multitasking, for example, combining inspection with other things. Fatigue, we all know how we feel when we're tired, and we don't make the best of decisions. And inspectors are very prone to fatigue, both visual fatigue as well as mental fatigue and physical fatigue. It's a very difficult job, frankly, and we need to factor that in. So, given the challenges of both visual search and decision making, how do we train visual inspectors? We can't just throw anybody in this job. It looks a lot more complicated than what you might have originally thought. And it's not just about telling them what's okay and not okay, or perhaps how to handle a part so it's not damaged. Well, again, we're limited in our time, but we have an 8-step process that's described in the book. And if you think through these steps as you read them on the slide, you'll discover that these follow very closely with a methodology of teaching hand-eye coordination that is referred to as training within industry. And I would encourage you, if you have some spare time, to Google search that term. You will discover that there's an institute. Scott Curtis is the current CEO of Training Within Industry, that organization. And it dates back to World War II and the methodology used to teach people who had never worked in a factory before to produce armament and things like that for the war effort. There's a couple points that I'll just emphasize and then quickly move on. It is absolutely vital that when you're doing training of any kind, that you establish and communicate what are the acceptable goals. What is the finish line look like for effectively trained inspectors? And that ought to be parsed in terms of both miss rate, false alarm rate, and pacing, because they're going to have to maintain those error rates at production speed. And many people do not measure effectiveness of training in those terms. But that is what you want, and that is what you must measure at the end of a training session. I strongly recommend, especially for visual inspectors, that you do a pre-training test, that you give them some sample parts to inspect, and you also give them a written test that might cover types of defects or where those defects might be located, or some aspects of the inspection choreography. What you want to do is tenderize these students, because people coming into inspection training already think they know how to inspect. It's easy. I just look for the defects. It's completely wrong. And they need to understand that. I've had people that worked at the company for 20 or 30 years get moved from a production job to an inspection job, and they think they know what they're doing, and they will be totally, totally wrong. And we need to help them understand that. Another thing, without going into great detail, is the fact that um, we all, believe it or not, we all get more lax in our inspection over time. The line between good and bad slides in the direction of miss rate. In other words, we accept more and more parts that would otherwise, if they were objectively evaluated, be rejected. Maybe that's entropy. Maybe it's the fact that you've passed some borderline parts and they didn't come back and nobody complained, and there's a greater push in manufacturing, especially, to pass parts than to reject them. Often there's a documentary kind of penalty for identifying bad parts. And so over time, the line between good and bad shifts. I used to think before I studied that people got crotchety as they got older in their inspection life, and they became more severe. Unfortunately, that's not the case. We all get more lax, and that's again very strongly indicated in the journals and research. We'll continue. So, what does world-class inspection management look like? Just to give you a big picture view of what things might be like if you were doing them all really well. First, you'd have a vigorous inspection certification program that would include confirming that the inspectors had the visual apparatus necessary. You would be shocked to discover how many people would fail a decent vision exam. And please don't trust the people that are doing driver's license examinations. In Indiana, you can be blind in one eye and 20/40 in the other and still drive a semi-trailer. So I'm sorry, but the possession of a driver's license means nothing with regard to vision testing. Another aspect is that when you take a vision test, that Snellen eye chart that you see about 20 foot away, it's not moving, right? Is your part moving while you're inspecting? Yes, it is, almost all the time. And so your ability to track is critically important. That's an aspect of vision and an aspect of visual performance that almost nobody checks unless they're informed about the criticality of it. We've talked about MSA and miss rate and false alarm rate measurement. We want to in an ongoing manner, monitor the individual performance, which means you need to have traceability to the inspector and the part, and traceability from that part when it gets accepted or rejected at the next process or at the customer back to that inspector. All of our parts are got a QR code on them. I know who inspected every one, and indeed I have a video of all of the inspection taking place, so I can review that video and find out when a part comes back whether they followed the inspection sequence or not. You might think that's a little Big Brotherish, but in our world, we want to remediate variances from the assigned choreography, and it really helps us because otherwise you're playing a whodunit game. Environmental factors around the inspection operation are critically important. I made, some seemingly jokes about, inspectors hearing things and then changing the way they inspect, but it's really absolutely 100% true. So you want to set up your inspection areas so that they're shielded from that. And of course, lighting is a whole nother subject we could spend an hour talking about. I do teach a two-day class for American Foundry Society on this subject, and there's probably 30 minutes of discussion about lighting. Ergonomics and how ergonomics of inspection impact fatigue, that's very important. The quality engineering of the visual search is also very important. Our work instructions, our standard work for inspection, needs to identify where the person puts their hands, how the part is located, where they start on the part, where they finish on the part, the path over which the eyes move. If you want inspection to be effective, the person has to see every area, and that means we have to help them plan their search routine. So many of my clients just don't do that. That's why they're asking for help. And then traceability and monitoring. And this is all not for the purpose of getting people fired. Inspectors are hard to come by. It's a very, very difficult job. People are hard to come by. So what we want to do is we want to do remediation. We want to help people see that they made an error and advise them and build good habits in them. And, no inspection operation is perfect. But the operation that we're running at the factory I'm working now, our miss rates are measured in ppm, not percent. So you can dramatically improve on the 80% effective number. I don't think we have an inspector that's below 95 to 97% effectiveness overall. You can do it. So what do I recommend you do as we wrap up this program? First is to measure inspection effectiveness objectively. Get a hold of a book on measurement system analysis. Learn how to do attribute inspection evaluation. Make sure your experimental size is pretty significant because attribute data is information poor. And so you're going to need to have a lot of data points in order to have a reasonable certainty of your numbers. Then when you get your miss rates and false alarm rates, and of course, you can also get an inter-rater agreement. You can use Cohen's kappa type statistics to evaluate their results against random chance. And you can get a pretty good picture of what your inspection is like. Once you do that, you can work with your accounting group to find out what that's costing you. And then you'll begin sobbing in your worksheets and really wondering if there's any hope. And that's when you start to do the following things on this slide. First, you want to make sure that inspectors understand what's okay and what's not okay clearly. That's the first place. The second is to work on an improved choreography so that they're actually seeing what they need to see and account for that visual lobe. And of course, there's guidance in, you can do the research that I did, or you can just buy my book, I guess. But plan a choreography so that, and you can use a physical 3x5 card if you actually hold your parts at an arm's length, and place that on the card, and then plan how many of those have to take place and in what order they ought to take place. And then multiply those by 0.3. Each 3x5 card is 0.3 of a second, and give yourself a tenth of a second in between them. Get training on the factors of influence, because this hour is nowhere near enough to help you understand the influence and some of the finer points of the factors. And particularly focus then also on training your inspectors, help them to understand some of these things, and help them to understand you're not chewing them out because they missed a lot of parts or were in trouble with a customer or something. You're trying to make their job easier. You're trying to help them feel better about what they're doing. Establish a certification program, really elevate your inspectors, because it really is a very professional, a very exacting, and a very demanding job. And then continue to improve, of course, because I love PDCA. We want to preach that closed feedback loop improvement. And that is my presentation. And we're right at an hour since we began.
Wow. Thank you, Ted. I'll tell you, we have had just a whole raft of questions pouring in here. This has been possibly some of the more questions than I've seen on any other talk this year. So I'm going to have to kind of pick and choose. I'm sorry, some of you asked good questions. As we've been saying, you'll get Ted's email address and you can send questions to Ted if we don't answer your question tonight. Okay. You will get a link to watch the recording, and you will get an email that documents your RUs. Okay, so let's go back through some questions here. Early on, you said the inspector assessing the rim intentionally rotated the rim towards her rather than away. Why? And is there an advantage?
Yeah, there is. Our eyes naturally track movement, and we want the eyes to follow that movement. And if we follow it away, what ends up happening is we tend to dwell on the horizon, on the profile of the wheel, instead of looking at the mass of the wheel. And so we tell the inspectors they have to look at the center of that object as it moves by their field of vision. Otherwise, they're going to track the edge.
Okay. So you mentioned that it's unacceptable to ask operators to do visual inspections during the manufacturing process. Why is this unacceptable?
Oh, well, let me clarify. I do not mean to say that in a work cell or in an operational sequence that you can't have both, say, a deburring operation or some assembly activity and an inspection. What I am saying is that those two things can't happen simultaneously. So, for example, our castings are worked on, they use a grinder to clean off the flashing. They think that they can inspect while they are performing the deflashing operation. Indeed, they cannot, because they're looking at something else. They're looking at the edge of their tool. They're looking at how much material has been removed and not the rest of the surface. And so we have to realize that what we see is very small compared to what we think we can capture as an inspection.
Okay. Um, so, talking about cameras here. Um, Recently, we did a change on the inspection method from magnifying glass to a camera, and this was done to improve the ergonomics and the quality of the process. Inspectors are reluctant to use the camera since they mentioned that it's taking more time to inspect than using a magnifying glass. What would your recommendation be to sell this idea to them? How do you think about that?
Well, um, so if they use a camera, I'm assuming that you're asking the inspector to view a video image of the camera output. And to me, just to me, the resolution of that image would be less than me personally using a magnifying glass, particularly one that has reasonable optics. And it also allows them, the inspector, the reason that they would prefer a magnifying glass is they get to move that magnifying glass the way they want to, not only side to side, but up and down to get maximum focus for their particular eyes. Honestly, if you can afford the time, um, I would use a magnifying glass. Now, the trick with a magnifying glass, and like circuit boards are often inspected. The solder joints are often inspected by human visual inspectors under lighted magnifying glasses, and I've worked with some clients that way. What you have to remember is that their field of view, the visual lobe, is very small under magnification, very small. And so an overlap methodology is critically important to do the best job of capturing any defects in that area.
Okay. Um, yeah, there's so many good questions. I hope we don't, guys, don't mind that we're going over our hour. Your recertification units will come in an email in 48 hours, so don't worry about that. Here's another question, Ted. Um, so, in selecting inspectors, is there an advantage to choose those candidates who have been certified with the downstream or upstream operations process compared to those who are detached from those operations and only dedicated to inspection?
Oh, well, I do think there's pros and cons to having people that think they know what's going on. Uh, because you do have to somewhat disabuse them of the notion that they're expert inspectors simply because they're good at prior operations. So,
Yeah.
that's the downside. Now, the plus side, if you get someone who has that knowledge, then they will naturally understand more about some facts that have to be taught inspectors. And again, we kind of skipped over this in our slide, but um, you have to teach inspectors the nomenclature for defects so that they name them the way that we understand them and that they have a consistent meaning. If one day this defect is a misrun and another time it's a flow mark and another time it's an inclusion, that's going to be a problem for problem solving and data collection and analysis. So they have to know the nomenclature. They have to be consistent in their naming practice. They also have to know where those defects are more likely to occur, so that they have awareness. It's a mechanism called feed forward. You want to help them have the most information possible about what's going on, and all those things experienced people from the production operations would have. But somebody that doesn't bring that, you'd have to teach those things.
Okay. Yeah. Let's see. Here's a kind of a complicated. Well, here's one on fatigue. Okay, I
Okay.
think that's valid. It says here, do you find as more focus is placed on fatigue for employees, that fatigue plays a factor in false accept and false reject rates? Any recommendations for the best mitigation for that?
Yes, I do. And to give you a uh, to put a capstone on that, United States Navy performed an experiment during World War II to try to find out how vigilance was affected by time on watch. So they wanted to know, how long should a duty watch be? And they discovered that after 45 minutes, vigilance, in other words, the percent of seeing important things, dropped by 50%. This was people looking for enemy submarines on Navy ships, a situation that has significant consequences. This is not like people were lazy or unmotivated. 45 minutes of focused search led to a drop of 50% in. So how do you deal with that? So the way inspectors deal with it is they take mini breaks. They inspect a few parts and then they talk to their neighbor, or they get another container or a package, or they walk around a little bit. They look aside, they think about something else for a while. They take mini breaks. But if you force people to do nothing but inspection for 45 minutes in a row, you will discover they are visually fatigued to the point where their effectiveness drops off like a cliff.
Wow.
So, what do? First of all, you do not penalize inspectors for taking mini breaks. Second, you rotate them, and if you can, I would rotate them to other duties. If inspection is all that they do, I would try to rotate them every hour or every 2 hours. We do it every 2.5 hours because the way we're set up, there's a break every 2.5 hours. So we put them on other duty because they do get visually fatigued. They get tired of making those decisions, and that's just human life. So what you want to do is you want to be able to have enough certified inspectors so that you can rotate them in and out of those jobs, and have them do other duties.
Okay. Let's do one more question. Okay. And there were actually two of these about color blindness. Many men have some level of color blindness.
Yeah, 8 to
How do you,
10%.
yeah, how do you consider when inspecting for parts with multiple colors like wires? What do you think about? What are your thoughts on that?
Well, first you've got to screen your applicants for color blindness. And there are standard plates that you can obtain. I believe they go by the name Ishikawa, not the Japanese quality guy, but there's another Ishikawa out there. But you can go online and get free plates, and as long as you print them with reasonably accurate color printer, you can use those, or you can purchase them at various outlets. That it's not so expensive. And then what you also want to do, and this is a whole nother subject, and I could spend a lot of time talking about, but when you do vision tests for employees, that's medical information. So that means certain people can't know all the details. I would recommend that your company nurse or an outside company perform the vision testing. And those people that do not pass the vision testing get recommended to go, and my view is the company ought to pay for this, to a optometrist or an ophthalmologist for professional evaluation. So you do a screening. Let's assume, for example, that they don't pass color vision. There are things that can be taught to a person to overcome color blindness, but there is nothing that I know of that fixes that problem to where the inspector would be able to discriminate in a wiring situation, for example. So in normal human life, it's pretty important to recognize colors. And so there's some things that can be taught to help them accommodate real life. But for an inspection scenario, color blindness for us excludes people.
Mm-hmm.
And one more thing about that, you say, well, my parts, they're all gray or they're black and white. There's no colors, doesn't matter. Yes, it does. Our depth perception is highly skewed in the direction of color cues. And so
Wow.
we will impact other aspects of our visual performance when we are colorblind.
Okay. Wow. Okay, Ted. I think we're going to have to wind this up now. This has been wonderful. Can you advance the slide, please?
Yes.
Okay, so here is Ted's contact information. We want to encourage you to reach out to him. You'll get an email in 48 hours. It will have Ted's email address, and you'll be able to contact him and ask him any questions that you have beyond that. This is his book. I've been putting a link to order this book in the chat region, so hopefully you got that. We'll put that in the email as well. Next slide, please. So we've got some webinars coming up. Quality Management Division we've got 3 of them listed here. July 27th, August 2, and August 16th. So we want to make sure if you want to register for these, you can use your cell phone and you can take a picture of these QR codes. We will also have it in our MyASQ site if you want to go there as well. So yeah, and next slide, please. So this is for Nick. Nick, you want to unmute?
Yes, sir. So hey, first off, Ted, great presentation. Really enjoyed it. Awesome stuff. Doug, thanks for inviting us in. From the inspection division, we'll be back on our second Tuesday of the month webinars next month. And on Tuesday, August 8th, we'll have Heather from ASQ Measurement, who many of y'all know, Heather Wade, talking about the elephant in the room or the impact of measurement uncertainty on risk. Always a great presentation from Heather for anyone that's seen her and heard her. And then on September 12th, we're going to do a state of the division, and the intent is also to do an overview of MyASQ. I think y'all all see everything. You can go to the inspection division MyASQ page under events, and I should have everything posted up there with links by I'm going to say Friday evening. So appreciate it.
Okay. Well, thanks, Nick. Ted, next slide. We want to remind people who are not ASQ members that by joining ASQ, get access to this and many, many other highly valuable resources. So again, there's a QR code there to find out about ASQ. Next slide. And we want to remind ASQ members that in MyASQ, Quality Management Division has a place there, as does the Inspection Division, but this is another QR code for people to go to that site as well. Last slide. Okay, we want to thank you, Quality Management Division and the Inspection Division. We thank all of you for coming to this talk and making this really successful. Again, you will get an email within 48 hours on this one. So let's